Hi there, welcome back. Now, one of the most frustrating situations when we are dealing with the estimation of the probability of default of a counterparty is the situation in which the data we have to estimate this probability of default contain no or almost no default. This is the typical case of low default portfolios. That is to say, portfolios in which, given the different types of counterparties we are considering, the number of defaults we have observed so far is negligible. And this actually creates problems in the reliability of the estimates we get for the probability of default of the different counterparties. Because you can imagine that we cannot really assume that since we have observed no default so far for a given type of counterparty, then the probability of that counterparty is actually zero. That will be a tremendous error. This is something that we want to avoid. Now, I have some good news and some bad news for you. Let's start with the good ones. The good ones is that actually there are methodologies that we can use, more or less heuristical methodologies that come from the use, for example, of expert judgments and Bayesian statistics, but also more simple consideration. And they give us ways of estimating the probability of default of a counterparty in the case of no or almost no historical default. These methodologies can be combined with the other things we have seen so far, with the other methods we have seen for estimating the PD of a group of counterparties. It can also be combined with methods that you use every day in your business life, like, for example, logistic regression or probit regression, so the different type of linear models you may want to use. So we can combine this possibility of estimating the probability of default of a counterparty when we don't have data about the default of that type of counterparty with the typical estimation methods we have seen so far. The bad news is that unfortunately there is no unique solution. So typically we may have quite different solution depending on the method we choose. And the best thing we can do is really to estimate these PDs according to the different methods and then try to make our evaluations by comparing them. The simplest starting point is to assume that the number of defaults for our counterparties follows a binomial distribution. The idea is that we consider n counterparties that are homogeneous in terms of probability of default, and the number of defaults we observe over time is just the result of n independent Bernoulli trials, where small p is the probability of default for each single counterparty, which is the same because we are assuming homogeneity for the counterparties. Now, the probability mass function of binomial is something that for sure you know. It's one of the basic distributions for discrete random variables, and you see this probability mass function on your screen. There we have exactly the probability of observing k defaults over n companies, where p is exactly the probability of default for each single company. Now, the point is that we can use maximum likelihood to estimate this small p, and it's easy to show that the maximum likelihood estimator for p is exactly k over n. Now, what's the point of this estimator? Consider the case in which k is actually 0, that is to say we have observed no default so far. Then it is obvious, it is immediate that p, the estimate of p, will be 0 as well, because p is estimated as k over n. So 0 divided by n is 0. Now you understand this is a problem, because This simple estimator tells us that since we have observed no default so far, then the probability of default is actually 0. And we know that this can be quite dangerous. A first estimator that we can use to overcome this situation induced by the simple MLE estimator is to assign some probability to the event of observing 0 defaults, and then to derive the probability of default from that. In other terms, we have our probability mass function, and we assume to observe 0 defaults, so k equal to 0. We can assign a probability c to that event, say 0.5, and then we can solve for small p, that is the probability of default we are interested in. In that case, the estimator will be 1 minus 0.5 to the power of 1 over n. This is the specific case in which we assume that the probability of observing 0 defaults is exactly 0.5. In the case in which we assume other probabilities, naturally our estimator will change. This estimator is an estimator that, paradoxically, despite its simplicity, is quite used in the explosive industry. We can then use the big family of Bayesian estimators, and here we can really produce a plethora of different estimators if we change our prior belief. Now let's start from the simplest case, and then you will find more details on the course platform. Let's assume, for example, that for the 0 default case, so that is to say when k is 0, we have observed no default, then we put prior on our parameter small p, the probability of default, of the uniform type. And then we have that the mean Bayes estimator for the probability of default is simply 1 over n plus 2. The derivation of this estimator is on the course platform with some more details. Another estimator, which is called the upper bound estimator, is used by those scholars according to which it is not logical that the p we can obtain in the case of 0 defaults may be larger than the one we can actually observe in the case of 1 default. In that case, what we can call really the upper bound, because this value we are using would be an upper bound for our probability, it's simply 1 over n. So very simple. Another possible estimator is the so-called confidence interval estimator, which relies on the basics of hypothesis testing. Given that we have observed 0 defaults, we look for the largest p hat we would fail to reject as an acceptable estimate of p. This is done by the usual Z standardization and solving for p. Z alpha is the standard normal quantile associated with a significance level alpha. The limitation of this method is due to the fact that the standard normal approximation typically works for a product of n and p greater than or equal to 6, using a common rule of thumb. In low default portfolios, n is usually small, therefore the approximation may fail. You see, it is not that easy to deal with this problem of no observations. What can we say if we compare these first estimators? From a qualitative point of view, the 4 estimators show similar performances. The confidence interval estimator A4 is usually the most conservative. Please notice that in the plot the x-axis scale is not respected. For the simple estimator A1, we have taken the probability of observing zero defaults to be 0.5, 50%. Changing this quantity, for example on the basis of experts' judgments, leads to different estimates. For example, for n equal to 4, if we set c equal to 0.1, then p hat equals 0.44. For c equal to 0.8, p hat is 0.05. Other estimators you may want to have a look at can be derived from the rule of 3, quite used in biostatistics and clinical trials, or estimators based on the common Poisson approximation of the binomial distribution and refinements given by the minimax criteria. Have a look at the papers I am uploading on the course platform. Many other estimators can be proposed, and it is almost impossible to consider all the possible estimators in a class. I'm posting extra materials on the course platform that I hope you may find interesting. In the next class, we will focus our attention a little bit more on Bayesian methods. Uh, but obviously, I'm here at your disposal if you have further questions. So again, please use the course forum. Please ask questions for the Casual Friday session. Goodbye.